Dr. Ashim, who has graciously agreed to address us today. Dr. Ashim is a distinguished scholar in the field of electrical engineering. He has received BTech degree in electrical engineering from Aligarh Muslim University, Aligarh in 2008, and MTech degree in power system from NIT Patna in 2012, and PhD in power engineering from Indian Institute of Technology, Kanpur in 2021. For a period of 2 years from 2008 to 2010, he was associated with Siemens Limited as project executive, where he looked into testing and commission of substation below 11 kilovolt of Delhi Airport Metro Express line. He joined NIT Patna as assistant professor in September 2022, where he is involved in teaching of undergraduate and postgraduate, and his research includes forecasting and its application in renewable energy integration and control, energy management in microgrid, and control and stability of grid forming inverters. On behalf of the department, faculty, I wholeheartedly welcome you, sir. We are truly honored to have you with us and look forward to giving valuable insight from your words. Most welcome, Dr. Asim, sir. You are most welcome. Please share your slide and start session, sir. Most welcome, sir. Sir, please unmute, sir.
Thank you for this introduction. Am I audible?
Yes, sir. Yes, sir. Audible, sir.
And is my screen visible?
Yes, sir. Yes, sir.
Welcome participants in this FDP Grace 20, PS 2025. I am Dr. Ashim, and I will be discussing with you on model order reduction and controller design for power systems. And we will be looking into the background of it from what is the theory behind this model order reduction, why do we actually do it, and how we can implement it in real life, and what are the different methods that are done in this model order reduction technique. To start with, this is our course outline. We will be looking into the introduction to the model order reduction technique, and we will be seeing the different methodologies taken, like balanced truncation or singular perturbations or model analysis, and thereafter we will move into how these are implemented into power systems. Some of the very simple examples we'll be looking into, and we will see how the controllers are designed, and simple codes will be shared with you, how they are implemented using MATLAB and the inbuilt functions that are present in the MATLAB. And we will now, after that, we will be now concluding our discussions on the topic of model order reduction. What exactly is a model order reduction? So, model order reduction is, as the name it says, that associated with any dynamical system, we will be having associated differential equations that will be capturing the dynamics of that system. For in context to power system, we are having synchronous generators. It is a dynamical system, and it has different states, and corresponding to that states, we are having differential equations. So now, depending upon the context of a study, the model of the synchronous generator will vary. Like if we are doing steady state analysis, we actually do not need that dynamical model of the synchronous generator. If we are doing load flow studies, then again we are not interested in the transients of that synchronous generator. But if we are studying these transient behaviors, then we are going into the differential equation mode of the synchronous generator, and thereby we are increasing the model of the overall power system. So, like, what exactly is model order reduction? The name suggests us that it is the reduction of the order of the model. So, order of the differential equation, if it is n, we will be trying to reduce that order to less than n without losing much of the information which are interested to us. Without losing that information, we will try to reduce the order of the model. So corresponding to these complex dynamical systems, we will be now reducing in such a way that the essential characteristics is preserved. The characteristics that are the point of interest for the research, for the interest of studies, that characteristics are held in the reduced model as well. So now when we look into the power system in general, we have like many generators. We have like dynamical, we have like loads, we have like transmission lines, control devices, we have like uh, additional reactive power devices, devices. So these accumulate the order of the system. By the addition of these devices, the order of the system builds on. It gradually adds on. Like say, for example, we are having a synchronous generator. For a transient study, we need at least like 6 to 8 states corresponding to like rotor angle, corresponding to the speed of the generator, corresponding to the flux linkages, the excited states. These like contributes to 6 to 8, depending upon how precise we are looking into the synchronous generator. These correspond to 6 to 8 states for a single generator unit. So suppose we are having a system where there are like hundreds of generators, like northern grid. So corresponding to only generators, we will be having like 600 to 800 states. And now if we include transmission lines, dynamics, 100 plus states, we will be getting a 1000 plus, because corresponding to 100 generator, we will be having like 600 to 800 states. And if transmission line models are also added on it, we are having like more than 1000 states. And like if we are adding those tracks devices that are placed at some discrete location within the grid, we are now again increasing to a very large number. So now when we try to model this for dynamical studies, point of studies, the dynamical studies of this large system, if we are trying to analyze or study the transient behavior, and if we try to model in a particular software, since the order of the system has now gone up to like more than 1000 states, these are like 1000 differential equations that needs to be solved, and we need 1000 initial conditions to have a defined dynamics of the complete system. So for a particular order for the available resources, computer resources and computational power, it's difficult to actually model the precise dynamics of this system and in the detailed dynamics of the system in real life. So what we do is that we first try to we first try to ask ourselves, what are we going to study for that system? What are the dynamical behavior we are interested in? Corresponding to that, we will be selecting the states that are more important to us, and we will be rejecting the states that are not important to us, under the condition that the overall behavior of the system is not deviated from the original system in the large. Obviously, if we are reducing something, we are trying to remove certain behavior. Certainly, the reduced model will be deviating from the original model, but that deviation should not be very large. Again, we will be trying to limit those deviations. So what are the advantage we will be getting for that? We will be like, if the order of the so it is a basic simple that if we are having a fourth order system, the controller design will be more difficult as compared to a second order system. As simple as that. So if you are reducing the uh, dimension of our overall power system, the controller design will be easy. And again, the basis of this model order reduction is that the physical behavior of the system do not deviate a lot from the actual behavior of the power system. So what exactly we will be looking into? The physical insight means that we will be looking into the oscillations that are having in the original system. We will be looking into that oscillation. We will be looking into the dominant oscillations, and we will be trying to preserve that dominant oscillations in our reduced modular system. We will be looking into the interaction between generators, those interactions that are critical to the overall power system. We will be trying to preserve that interaction in our reduced model system. We will be trying to look into the what are the bottlenecks, what are the weak points in the power system, and we will trying to capture those weak points that may cause system to go into instability. We trying to those sensitive information and trying to carry on those information to our reduced model system. By doing these model order reduction, as the order of the system is reduced. So if we are working on this, like we are working on the original system, the order is very high. So suppose we want to develop a controller, we want to design a controller for that, and the parameter tuning will be a bit difficult. Like if the order is high, the corresponding controller parameter. If you are using some optimization techniques, these meta heuristic techniques like GAPSO, in order to tune this controller, so it might happen that these large number of states might lead to uh, lack of convergence of this optimization algorithm. So what will happen is that the controller tuning will be a big problem for the detailed modular system. And as soon as we try to reduce it, the state of the power system reduces, and this what it leads to is that the tuning of this controller will become a bit easy. So these are like advantages we carry with when we are reducing the model. We are actually limiting, we are actually what you call reducing the computational burden of our uh, available computational resources. We are reducing the burden, and thereby we are in condition to that, while reducing it, we are not again losing the information, critical information. So these are like background. What are the basic need, and what are the basic benefits we are getting after reducing particular model. So these are like the state variables, like these are associated state variables for a large system. As the states are increasing, so are the complexities of the systems are increasing, and thereby the controller designs are increasing. The controller designs are becoming difficult. The, at an additional cost of like increased dynamics of the system. So there are like certain dynamics that can be rejected. They are like not important for the study, but these critical dynamics are preserved in model in the reduced model, and thereby the computational resources needed to run these reduced models are again in the limit of the available resources. So like when we talk about the model order reduction, uh, the fundamental requirement of a model to be reduced is that model should be linear. Uh, Linear time invariant system can only be reduced. So when we look into our present uh, model of power system, we see that this model is actually non-linear in nature. So what is the problem or what is the requirement before reducing the model is that we need to actually we need to actually linearize our present power system model. So when we are going to linearize it, what is actually happening is that linearized model of a power system is only applicable. Linearized model of the power system is only applicable at the point of linearization only. So if we are having, like, say, we want to linearize a model of a power system, we do the load flow analysis and we try to find the operating point of the power system, and around that operating point, in a very close proximity of that operating point, we linearize that model. So this linearized model is only valid for that particular state, around that particular steady state point. Suppose the behavior of the power system has changed. So if the steady state condition of the power system has changed, we need to do this linearization again. So this is the disadvantage of like model order reduction, is that if we are working with a non-linear model, we need to do the linearization as often as the steady state behavior of the power system changes. This is the problem or limitation of this model order reduction, is that it works on the linearized model. So like, if we look into this LTI system state space model, we are having these ABCD parameters corresponding to these states. The derivative of states are related with the actual state and the input of the power system, US. The states are the x's, and it's related with these standard state space model, where we are having, like, A is the system matrix, B is the input matrix, C is the output matrix, D is the feed forward or feed through or direct transition matrix. So through these matrices, we can find the output. The output is related to the input through a different, and we can convert this state space model into the transfer function model with the formula of GS as given here. Now, what we are actually doing, GS is the actual transfer function of the detailed model in the linearized term. If we are working with a non-linear model, so GS is the linearized transfer function of our non-linear power system model. And what we are doing with the reduced order model is that we are reducing the overall system. Thereby, we are changing the transfer function of the system, where GR is the reduced order transfer function. So what we are doing is that we are interested in the reduced order model system in such a way that the infinity norm of the actual system and the deviation of the infinity norm of the actual system and the reduced order system is less than a predefined minimum value. This is actually, we need to respect this condition, this particular condition, we need to respect it at all times. So now we are looking into what are the approaches that we take when we do these model order reduction. So basically, there are like three methods. So first one is the balanced truncation method. So balanced truncation method is like what we do. So the bigger picture is that we are having a power system model that is non-linear. We have linearized it. Now the linearized power system model will be having controllability and observability matrix. We try to balance this out. We actually looked into the reduced order model. The behavior of the reduced order model, behavior in the sense of this controllability and observability, should not deviate much. Again, we are again predefining this. It should not deviate much from the original model. So what we do is that we calculate these grammings, the controllability grammings and the observability grammings. So, so what exactly these grammings tells us? So the controllability grammings actually, it says that for a particular state, The value of this, it will mean that it gives that how the states can be controlled through the input. What is at how easily we can actually control. So a measure is in the form of this, how easily we can control the states of the system through input. So that is like a physical interpretation of the controllability grammar. And observability grammar, it says that how easily we can observe or measure the states from the output side. From the output side, how easily can we measure it? So if we look into these error bounds, we actually one of the objectives is that we need to preserve the accuracy, accuracy of the reduced model system. The reduced model system should be like it should accurately represent the input or the behavior of the original system. So up to how much level? Up to the range of up to the frequency range or the of our point of interest. How so corresponding to these frequency range, we are actually looking into the dynamics of the system. So how close or what sort of dynamics are we interested in the study? Corresponding to these dynamics, a bandwidth will be our like point of interest. Corresponding to this bandwidth, we will be having like what is the lower limit of the frequency of the study, what is the upper limit of frequency of the study. Within this frequency limit or the bandwidth, we want that the actual model and the reduced order model should not deviate much. It should actually map each other. Uh, we also need to have the stability, uh, preservation of stability, that the reduced order system should be stable. If the original system is stable for that frequency variation, the reduced order system should also be stable. And and also we want to see if there are like n states in a particular power system, so all the n states are not important. There are like some very important, very critical mode of oscillation. There are like least important, or we can like ignore it. So those important states of the information should be carried into the reduced order system. And if we are like uh, studying different time frame dynamics, suppose we are studying like electromagnetic transients, or if we are studying like electromechanical transients. So electromagnetic transients are very fast transients. It is in the order of like milliseconds and microseconds, while electromechanical transients are like in the order of seconds. So the behavior, it is not that these electromechanical transients are least important and electromagnetic transients, because it is fast, it is more important. We need that the behavior of the system, if there are some important mode of oscillation that is existing in electromagnetic on electromagnetic level in microsecond to millisecond. If that mode of oscillation is important, we need to capture it. And if there are some modes that are important and that is present in electromechanical, that is, it is of the order of second, but it is important. We need to capture both these informations in our reduced order system. So, so these are like the basics of this balanced translation. What sort of information we will be capturing and what sort of information we will be rejecting. We will be calculating the grammings. We will be now then solving this Lyapunov equation, the equation that is given here. So these Lyapunov equations are like solved in different ways. There are ways depending upon the complexity of system. We can use like direct method, what we call as Kronecker product method. We can use that method. We can use iterative method. We can use low rank method. These again like depends upon what are the dimension of our power system. So when we solve these Lyapunov equations, we come up with actually WC and WO, the controllability gramming and the observability gramming. Then we calculate what is known as the Hankel similar value. So what Hankel similar value says is that uh, we need to actually calculate using the formula like lambda I times WC into WL, like this in this way, where WC and WO are already found out using Lyapunov equation. Lambda I are the eigenvalue. So lambda I are the eigenvalue, and it is calculated from the system matrix. The system matrix, if you look into these, the lambda i's are the eigenvalues corresponding to this A. So when we calculate this lambda sigma I, which is Hankel singular value, uh, the value of sigma I, the value of this Hankel singular value, it suggests or it has this information is that if the value is large, if sigma I is large, that means sigma is large. Mind it, if sigma I, ith angular value is large, that means that particular state is highly controllable and highly observable. And if sigma is low, that means that uh, state is least controllable and least observable. That means what does actually that means is that if the state is highly controllable, that means the input has more control over uh, state, not state wide, dynamics of the states. Input has more control over the dynamics of the state, a sense of controllability. So if sigma I is high, the input can easily control the states. And again, if sigma I is high, the output can easily measure the state as well. Output can easily observe the state or measure the state. Sigma I is low, the input and output has least effect on the state of the matrix if sigma I is low. And if sigma I is zero, that means either the state is uncontrollable or the state is unobservable. Because if sigma I is zero, then from the formula we can say that either WC is zero or WO is zero. Okay. So what we do is we in balanced realization or in balanced truncation, what we do is that we looked into the contribution of the ith state, and then we select certain states and reject certain states such that it again this respect this error bound, and this error bound is predefined before what we actually start doing this. We define this that the error bound, that means the error bound between the transfer function of the actual power system, the error bound between the transfer function of the actual power system and the reduced power system. So we are talking about the H infinity norm or like DC gain of the system. It should be bounded. It should be bounded. There is an predefined bound on that error. So like this gives us like balanced realization or balance truncation give us a reduced order model for our given power system. So what we are doing, we are taking the Lyapunov equation, we are computing the Hankel, we are this one, we are calculating the transformed value. This WC balanced and WO balance is the transformed value. So what we are doing, we are actually taking our initial system, linearized power system, the formula one and the equation 1 and 2. The system is defined in the form of equation 1 and 2, and in balanced WC balance and WO balance, we are transforming our controllability gramming and observability gramming such that WC and WO are a diagonal matrix, and the values of the diagonal elements are the Hankel similar value of our original. If you look into this equation, balanced and the WO balance is equals to diagonal sigma I. So this is the condition we try to achieve. Uh, the WC balance, WO balance should be equal, and that should be equal to our matrix whose diagonal elements are the Hankel similar value. So these are like standard approaches where we have a very standard way of doing. And when we arrive at the reduced or balanced WC and WO, we then partition our state space model. And we say that this X2 is are the states that are rejected and that are having very less effect on the overall behavior. By rejecting that state, we are getting a transfer function, a reduced or transfer function that is having a finite deviation, bounded deviation from the actual power system, actual transfer function of the complete power system of this term. So what we are doing in this in partition truncation, we are keeping x2 as 0. So x2 corresponds to all those bunch of states. X1 corresponds to all those bunch of states that are preserved. So x1 is certainly not 1 cross 1. It is like if we are having n order of the original power system, x1 is like R. We are taking R states, and x2 is like n minus R. We are rejecting n minus R states. So these are the states that have least contribution. Least contribution, by mean least contribution, is that these states are having very less value of sigma I, and we are rejecting these values with the condition that these states are neither controllable or not observable. These states are least controllable and least observable. By less value of sigma I, we mean these are less controllable and less observable. And thus we obtained our reduced order model. So if you see, so x1 dot is x1 is the dimension of x1 is like R, which is less than n. So like this is a typical fourth order single machine infinite bus system where the dimension of A and B is given. So through this we like calculate Hankel similar values. Again, these are the calculation of most of the part will be like directly calculated. We do not need to actually do some coding. Rather, there are like inbuilt functions in the MATLAB that will calculate all those things. What we are trying to actually highlight here is that the Hankel values are like they are corresponding to these 4+4 matrix. That means we are having a fourth order system. The Hankel value says that the 4 sigma I, sigma 1, sigma 2, sigma 3, and sigma 4 are like 2.45, 0.83, 0.15, 0.02. What we are doing, what we're seeing from this is that there are two sigma I that are having much less value as compared to the rest of the two. We are safely removing with the condition that the error bound is like twice into summation of sigma i's. If we look into the previous formula, error bound formula, this formula, we will see that the values are like R states are preserved. If we were talking about n states, in that n states we were saving the R state and we were rejecting the n minus R state. So R plus 1 to the end of the states are the rejected states. So the summation of the singular values are the deviation should be less than twice the summation of the singular values or rejected singular values. We get error bound as 0.34 while the actual error bound is less than or almost equals to 0.32. So what we are seeing that the two states are removed safely, and as the two states are removed, the dimension of the transfer function order will be like second order transfer function, and corresponding we will be having a control and easy to approximate the constants of the controller. We can like calculate in a comparatively more in easier way as compared to a fourth order system. Now we are going into the what we call as the second method. What is the second method? So second method is like a singular perturbation method. So in singular perturbation method is that we are having um, again different dynamical behavior. Right? Some states are very fast, some states are slow, and there is like a so in that condition, suppose we are having a state in the power system that is very fast. So so the fast transients will die out early. However, the slow transients will um, remain in the system up to a large extent of time. What is happening is that uh, in singular perturbation theory, what we do is that um, we this is actually relevant to the power system where we are having this gap between these dynamical behavior. That there is a set of states that is too fast, and there is a set of states that is comparatively slow. So we break our state space model into these two states. Like equation number 9, we are having all those states corresponding to flow dynamics, and equation number 10 is like all those states where we are having fast, and this eta is the time scale separation parameter. This is defining our slower states and the fast states. What we are doing is that we are taking like quasi steady state approximation. What does that mean? It means that if uh, if you a particular state is fast as compared to the other states, that means it will reach a steady state much early. However, there will be some transients in the slow states as well. As you see, the red line is showing. Actually, it is now like drawn by hand or drawn. It is not actual dynamical system captured from the other. Just to explain you, the red line is now like uh, about to settle. However, there is the dynamics still existing in the blue line. So what we do is that we uh, keep it as zero. The uh, sigma xf, this part, sigma xf is the fast dynamics. The dynamics will be like exhausted. The dynamical behavior will like goes to zero. The dynamics will be zero. Even if there is dynamics in excess, we are keeping it as zero, and then we are solving it. So the states, excess states or the fast state can be estimated in this way. Excess can be estimated safely. Then what we are doing, we are taking these excess states and then we are putting in our flow dynamics to obtain our reduced order model system. So how this model is reduced? You will see that the fast dynamics are XF are estimated using the dynamics of the slow states or slow dynamical states. And the overall dimension, if you look into is this dynamical equation, this is the reduced order model. So what is the dynamic? What is the order of the system? Excesses are only those states that are slow. And this states is again like capturing the information of the fast state and approximate information of the fastest state using equation xf equals to minus a to 2 inverse multiplied by this. If we calculate this excess from equation number 11 and put into the above equation, we will calculate the state of xf safely. So this is again like a method where we are reducing the overall state. So total state of the system was equal to xs plus xf, where we are having certain states that are slow considerably slow as compared to a set of states except that are considerably fast. So the objective or uh, the philosophy behind this model or reduction was that in singular perturbation, we are taking all those states that are fast with the assumption that the dynamics in the slow states are still existing. However, the dynamics in the fast states have died out. If the dynamics have died out, there is no dynamical behavior in the system, then the derivative of the states is zero. This is the so if there are no dynamics means the system has reached the steady state. So that fast state has already reached the steady state. So this xf is like kept at xf dot is like kept at zero. Xf dot is kept at zero, then we can safely calculate xf. So now xf is known when xs is known. Xs, the slow dynamics. Slow dynamics is known. So slow dynamics is known using the above equation. So using the above equation, we calculate the slow dynamics and then we use that slow dynamics to calculate the fast dynamics. So overall state of the system is now reduced to only the slow dynamical behavior. And the fast dynamical behaviors are estimated using the slow dynamical behavior. Obviously, there will be some deviation again, where there will be some deviation between these, the actual model and this reduced order model. But again, these deviation has to be uh, bounded by a limit. Suppose we are taking this single machine infinite bus system, and we are also now using a fast exciter dynamics. So if you look in equation number 17, this corresponds to fast dynamics. This corresponds to fast dynamics means the time constant of the two. The time constant of the two will be very high, or depending upon the ratio, it will be very low or very high. So this corresponds to actually the slow dynamics corresponds to these mechanical. Again, these are clubbed. Mechanical and electricals are clubbed into slow dynamics, even if their electrical is almost 10 times or 100 times faster than the mechanical dynamics of a synchronous generator. For sure, it is 10 times faster. For sure, it might be 100 times faster. So these two dynamics are actually clubbed in one, and the exciter dynamics are much faster than the electrical. The faster of the slower dynamics, it is much faster than these two slow dynamics. In such a way that the slow dynamics is still in transients. However, the fast dynamics has already reached the steady state. So this error is like should be much less than one. Not error. The time separation parameter. The parameter that is actually this boundary layer. That is splitting this fast dynamics TF and the slow dynamics TS. That should be that boundary. The ratio of this time function should be much less than much less than one. So the error is now estimated as 1.7% based on the value of E. 0.017 multiplied by 100% give 1.7% error. So that means that the states of the exciter, if it is estimated using the state of the slower dynamic, the state will have certain error, and that error will be like very less. So we can ignore the very fast dynamics of the exciter system. So we are having if there is some like error in this because the electromagnetic system is kept at very high. So we are having like electromechanical system and exciter system very fast. So we are reducing the states and corresponding reducing the overall dynamics of the system. The third one corresponds to the model analysis and truncation. So what we do in model analysis is that we exploit the model structure of the system matrix. So model structure of the system matrix, that means we are actually looking into the system matrix. What exactly is the system matrix? System matrix is relating the dynamics of the state with the actual value of the state. So system matrix is this one. System matrix is A that relates this derivative of the state with the actual states. We are using this A matrix, and then we are actually again we are. So if you look into this V inverted V inverse, these are like mm, uh, eigenvectors. V is the what you call as the right eigenvector of matrix A. V inverse is the left eigenvector, and this inverted V is the matrix, diagonal matrix of the eigenvalue. So basically, what we are doing is that using this V inverted V inverse, we are transforming our state matrix into another dimension in such a way that this state X and this state Z, this state X is like a coupled states, and this state Z is a decoupled state. So by coupled states and decoupled states, we mean that if a state is coupled, that means the dynamics of a particular state will depend upon the rest of the states. So if we are working on a coupled system, and suppose if we are having two states, then the dynamics of state one will depend upon the value of state one and two. So we will say that this is a coupled system. So analysis of a coupled system is a bit difficult, a bit non-intuitive as compared to decoupled states. So by decoupled states, we mean that the dynamics of the states depend upon the value of that states only and independent of the value of the other state. So much easy to analyze, much easy to visualize, because we are changing. If we transform a particular state space model, the state matrix A, from a coupled system to a decoupled system, then we can easily say that if we are varying this modified states, say for example Z1, then we are sure that we will be only changing the dynamics of the state of Z1. If we are modifying this transformed state Z2, we are only modifying the dynamics of that state. Because the system is decoupled, Z2 is not influencing the dynamics of Z1, and Z1 is not influencing the dynamics of Z2. The system is decoupled. However, this is not true for a coupled system or our initial state space model. Initial state matrix A, that was a coupled system. So X1 and X2 was coupled. That means the variation in X2 was influencing the state dynamics X1 as well. It was influencing its own state, and it was also influencing the other states as well. The variation in X1 was influencing its own state, and it was influencing the other state as well. So what we do in that is that we now use a transformation matrix, V inverse, and through this transformation matrix, we decouple our states, and then we transform this state space model X dot is equals to Ax plus Bu into Z dot is equals to inverted V Z plus V inverse Bu. So this what you call as this decoupled states. So this decoupled states, we will be estimating a participation factor. Participation factor is of a particular state. For a particular state, we will be calculating the participation factor using this right eigenvalue, right eigenvector, and left eigenvector. And the value of participation factor, it will like give us a sense that what sort of states are more contributing in the dynamics. If the value of participation factor is high, we will be saying that as so high and low are like relative terms. So corresponding to two states, if the participation factor of one state is high, we will be saying that this state is actually contributing to the dynamics of the overall power system more as compared to a state whose participation factor is less. Based on that, we will be like rejecting certain states whose participation factor will be less, and we will be uh, uh, taking all those states whose participation factor is more. Again, objective will be reduced order system. The transfer function of the reduced order system should not deviate much. So we will be actually uh, predefining the error, and then we will be into this reduction of the states based upon this participation factor. A sense that a value, participation factor is a value that gives us a sense that which state is contributing more. A high value participation factor will say that that state is has a more contribution to the overall dynamics of the power system as compared to a value of a state a value of a state whose participation factor is less. So based on this, we will be having like different modes again, like uh, local mode of oscillations. We will be having inter-area mode of oscillations. We will be having control mode. So based on this, we will be doing this analysis. So now come to this participation factor. So the how it is calculated? It is calculated using right eigenvectors and left eigenvectors. And again, the value of this, if the value of this pi is high, we say that the participation factor. And again, we will be like normalizing this just to have a better picture of it. We will be normalizing this participation factor, dividing the participation by factor by. So the actual participation factor will be divided by the sum of the participation factor to keep the sum of all the participation factor equals to 1. So in this way, we will be like seeing if suppose we are having P11 as 0.85, P21 as 0.82, and P3. So these are like high values. So if we look into this small graph associated or figure, the color that is dark is actually representing a high value as compared to a color that is very low. We can safely reject the states that are contributing less or whose participation factor is less. So certainly these extreme right column and below left two rows can be safely like removed, and most of the informations are captured in these dark color uh, rectangles that corresponds to high value of participation factor. Now these are like what we initially talked about, that if we are studying a particular system, the study, the level of a study will define that what sort of model we are into. So if we look into classical second order system, basically we are using it for load flow analysis, load frequency analysis. This model is simply for load analysis. Again, like if you are into the transient behavior, more detailed transient behavior, we will be using like detailed model, fixed order model. And again, if we are still into higher, because if we have to study those very fast voltage regulator or power system stabilizer or controller, additional states are now adding on, and these states are like for a single generator, these 6 states plus additional AVR and PSS, one or two, one at least one state more. So like 7 or 8 states will be for a single generator. And as we discussed earlier, if we are having like multiple generators, suppose like we are having 3 machines. So corresponding to these 3 machines, we will be having like 6 states for each machine and corresponding control. So at least we will be having like 24 states, 18 states associated with machines, and we will be having like six, three states for each control action. Thereby, we are having like 24 states corresponding to these three machines, and we are not calculating the states that are associated with loads and transmission lines, and if we are if we are using some reactive power source like fax devices or capacitor bank. So we are not actually looking into all those. So what the overall state matrix of this system will be like, there will be some values very less, or this matrix will be sparse in or structure. So some values will be zero, some values will be less, and some values will be more corresponding to these uh, dynamical relations. So what we will be doing is that we will be rejecting these sparse information based upon these three actually approaches we talked about. Either we will be using these balanced truncation where we will be calculating these Hankel value, or we will be using, if we are having like fast voltage regulators, then we will be using those slow dynamics and fast dynamics. We will be creating a boundary between these two uh, time scales, and we will be estimating the fast states based upon the values of the slow states, rather doing the dynamical studies of these fast states. We will be actually keeping except dot zero. So we are not interested in the dynamical behavior of fast states. Rather, we will be estimating the fast states with the values of the slow states. This is one approach. The third approach will be, we will be actually calculating the participation factor, and we will be keeping all those high value of participation factor and rejecting all those low values of participation factor with the condition that uh, with the information or presumption that high value of participation factor is actually contributing to the dynamics of the state, and the low value of participation factor is least contributing to the dynamical values of the overall power system. So now we are actually looking into what are the non-linearities available or happening in the power system. So this is the power flow equations. Again, this is a non-linear form of the equation. So if you are, or if we are actually going for a model order reduction, then we will be actually reducing uh, this nonlinear equation into a linearized form. For that, we will be actually solving the load flow equation. Load flow equation is solved to obtain the steady state behavior of the power system, and at that steady state behavior, we will be linearizing it with the standard Taylor series expansion, where we will be uh, keeping the first order term only, and we will be rejecting the second order term because the objective is to linearize it. So only the first order term is, or the first order term is linear, and the less higher order term is again linear. We will be rejecting it. So these linearized model, uh, again, so with this linearization, actually what we are doing is that we are limiting our point of operation. So if the point of operation is changing, we again have to linearize it. But this linearized model is suitable to study or suitable for model or reduction, with the condition that it can be studied only at that point of interest where we have linearized the system. So suppose this is a particular example where we have like taken a single machine finite bus system. These are some of the values. We have seen the A matrix, we have seen the Hankel similar value, we have reduced the error, we have estimated the error. The addition of these two, 0.15 plus 0.02, that is 0.17, twice the 0.17. So error bound is this, the actual error was 0.32. If you observe this, the dynamics of the state with respect to time, you see that the original system and the reduced system is almost equal. This almost means that the bounded system, the dynamics, the deviation in the dynamics is bounded. The deviation in the dynamics of original system and the reduced systems is bounded. Deviation is bounded. These are like we are actually looking or we are doing the single perturbation method, where we are having an exciter that is having much faster response as compared to the electromechanical part of the machine, and the state of the exciters, the dynamical states are not studied using differential equation, rather the dynamics of the exciter or the state of the exciter is estimated using the uh, states of the slower order dynamics. We have looked into that particular equation. So just to recap it, what we are doing using this equation, what we are doing, we are calculating the fast order states, all those states that are very fast, using the values of the slow order state, rather solving this equation, rather solving this dynamical equation, we are estimating the states of the fast order system from the slow order dynamics. So if you are removing these states, again, we are reducing the dimension of the overall dynamical system. Okay, so I hope I am not very fast and I am trying to make the thing as easy as possible. So this is like the uh, 9 bus system. We are having three generators and 9 bus. We are having 12 states, four power state, and these are like frequency range and all those modes that are less than 10 hertz are accepted. We are calculating actually this is in this we are calculating the participation factor. Thereby, we are retaining some sort of information. We are rejecting some sort of info. So at this point of time, we are accepting all those states that have the dynamics less than 10 hertz. That corresponds to 10 hertz or less. We are keeping, and all those fast we are rejecting. Now comes the controller design. So there are like basically two approaches in controller design. There are like two approaches. Is the first approach is that we can have uh, reduce the model. So if we are having a model of very high dimension, uh, large number of states, what we do is that we first reduce the model. We reduce the model and then we design the controller. So that is the controller is designed for the reduced model. So now as the model is, uh, again looking back into these model or reduction techniques, uh, the deviation or the H infinity norms are bounded. The deviation between the actual power system, the deviation between the transfer function of the active power system and the reduced power system. The H infinite norm is it's bounded. It is less than a value epsilon, much less a smaller value, predefined smaller value. The second is like we design controller for full model and then reduce the controller. There are like more advantage to step number one because uh, step number one, what we are doing is that we are reducing the model, so the controller design become much easier. So just if the plant order is less, so we can use those beta heuristic optimization technique to calculate the values of these controller. So these can be like, since these are iterative process, so these the convergence will be fast and ensure it will ensure that the system will converge. The optimization uh, algorithm will converge. But if the plant order is high, there are large number of states where there may come a possibility that these meta heuristic algorithms do not converge to a point, and we might not get a values or we might not get the controller uh, tuned values of the controller. Uh, so the associated challenges is that as we have now reduced the model, there is a possibility that we might miss some dynamics, but it's again less. Again, robustness question is are questionable because the system might be stable. The reuse or order system might be stable, but whether it is robust or not, we cannot be very much sure. There is a small amount of performance degradation, obviously, because we have reduced the model, so we have just deviated from the actual dynamics of the system. But again, like overall, if we look into these two approaches, uh, uh, reducing the dimension of the plant and then doing the controller design is much easier than doing the controller design and reducing the order of the controller. Because in the second part, there might come a possibility, there might be a possibility that you might not even get the value of the tuned value of the parameter. So most of the time, approach ones are uh, used, and uh, what this line is saying that if you are working or if you are working with a reduced model order reduction approach, you are using it, then we must actually show this result that our system, the actual system and the reduced model order system, the dynamics of both the systems are same. And if you are using some controller to tune or controller, if you are using some controller to control the dynamics of the system, then we have to actually implement control action in both the detailed model and the reduced model and show that the control action is almost same, because these two results have to be shown in, if we are doing some classroom teaching or we are doing some, if we are presenting some results somewhere, we need to show that these first result, the reduced order model and the original model is same for our system. Not same, it is similar. The original system and the reduced system is similar, and the effect of control action on original system and the reduced system is similar. You need to show. Okay, so like these are some of the problem we come up with based upon the initial 4x4 model, SMIB model. We have reduced into second order. Corresponding to that, the plant transfer function was that we used the PID controller and found these values to be optimized, an optimized value. And with this, we have found the like settling time of 1.8 and maximum overshoot of 8.5 on the reduced order model system. Here I haven't shown on the actual system, but this has to be shown. So the control action on both the reduced order system and the actual system has to be shown in the research article or in the class to ensure that both the controller is effective for, ultimately the controller has to be effective or has to be uh, placed for the complete system. So we are working with the reduced order system, but actually the controller will be placed in the actual system. So we need to ensure that the control actions are similar. We can now, again, like this is an approach in model control theory. We can use a state feedback controller design, and we can, this was like hit and trial method where we try to optimize the parameter using some of the beta heuristic or algorithm, where we keep those cost function like ITAE error and or some other integral of the error as minimum as possible. So this was one approach. The other was we might take those uh, state feedback controller design that are standard design techniques for giving the parameter. Usually state feedback in model control uses that we uses those state space model. So again, if you look into this, we are actually looking into those flow dynamics, and thereby we are controlling the states. We're using only this equation and rejecting all those fast dynamics. So for pole placement technique using state feedback, we actually have to give that this is the desired pole. Now, this desired pole, where does this value come? This values come from the performance setting. What is the desired performance? So if the desired performance setting, like if we need to have a settling time of 1.5 second overshoot of this and steady state zero, this will reflect into that the pole of the system should be at this place. So if the pole of the system has to be at this place, then what should be the uh, particularly gain of the controller. The gain of the controller should be like this. Overall pole of the system. What was the initial pole? The initial pole can found using uh, this equation. This is the one of the state space equation. The next is the output equation. Using these two, this the first equation and the output equation, we can calculate the transfer function. So the transfer function will give a particular value of the states. So these states have to be moved to this desired state. Since we started with fourth order system and reduced this to two order system, the transfer function will be a second order. We are having two states corresponding to these equations. These state has to be moved to this particular state. For that, you keep these three gain values and then we calculate the overall performance. Okay, so like these are the MATLAB codes. You can also test it. Using this with the values of A, B, and C. So steady state model was calculated using this equation, and then we have the reduced Hankel singular value is calculated, system reduced system is calculated like balance reduction. Balance reduction, and we are reducing this fourth order model to second order model, and then we are calculating the error bound, and then we are calculating the actual error. What is the error bound? What is the actual error? Is the H infinity norm between the system and the reduced order system. So these are like standard function that is available in the MATLAB. And then we are calculating this. I mean, we need to validate the actual system and the reduced order system should be comparable. It should be, the error should be, the error in the dynamics should be bounded. So we calculated both the body plot, the frequency analysis, and we calculated the step plot, that is the time analysis. With both the frequency domain and the time domain will be calculated, and we validate using these two. And these are some of the inbuilt MATLAB functions you might use to actually solve these model order reduction. So this is like balance reduction. This is like H infinity norm to calculate the deviation between the actual transfer function and the reduced transfer function. H infinity norm should be less than the formula we have actually looked into. This is like solving those Lyapunov equations. Two Lyapunov equations to calculate the controllability Grammy and the observability Grammy that give us a sense of how the input state, how the state of the systems are actually controlled through inputs and these Grammys like, and how the state of the systems can be measured through the output. So these actually give us, so we can solve these Lyapunov to actually calculate this WC and WO. And when we calculate this WC and WO, we then can calculate this HSV, Hankel single value. HSV is like under root of lambda I into WC into W. Then we can now calculate the eigenvalue of any matrix by using this formula. We can calculate, or we can actually draw the step plot using this and the body plot using these functions. And then this is the like output of our this previous code. So what we got is that all the error bounds are satisfied, and the theoretical part or the actual part and the theoretical part means theoretical calculation and distribution. These are like they match each other, and what we observed from this study is that our performance is preserved. So now when we actually do this analysis for a new problem, these are some of the plots we wish to actually draw. Hankel singular values or body plots with phase comparison, step impulse response, error analysis, pole zero map, model distribution, time zero. So these are different plots we need to actually draw for a particular system, the original systems and the reduced order system. So again, like we will be like seeing this what are the robust model reduction. So if there is like change in the inertia, so how does this change actually get into our inertia? This is the point. So for a particular power system, estimating the inertia in itself is a problem. We actually do this if we look into the problem of load frequency control. We do this single area to area and then we use this transfer function 1 upon 2hs plus d. We now give this value of h into the power system. But how come we know that this is the h? This is the inertia of the overall power system, because inertia in itself is a problem, not problem. Estimation of inertia is itself a research problem in a particular power system. What is the value of it? So if you are trying to estimate the inertia, there is a possibility, and there is a possibility that your estimation will be off by certain, because we are estimating it is, there will be certain error, or there will be certain error into the estimation. So in load variation, the load is changing. Again, from generator side, we are trying to estimate what is the load at the consumer side. Again, when we are estimating the load, there is always a possibility of uh, deviation between the actual load and the estimated load. So these are the two causes where we are having the deviation in the actual inertia and in the actual load, because we are actually estimating the inertia, we are actually estimating the load from generator side of point of view we are talking about. So what will be the robust approach for model order reduction? We will be like, there are different actually methods. There is like worst case model order, probabilistic model order, multi-point model order. Or again, this is, we will not be going into, but I'm just trying to introduce it. So these are the available, and someone can look into if they are interested in actually exploring this area. So these are like some of the model order reduction techniques that are robust in nature. These are like some uh, real application. We have talked in the very beginning that for a real power system, we will be having a very large number of states. So this is like Nordic test system, 74 buses, 20 generators. So like 20 generators, 6 state, at least 6 state for generators, and there will be associated AVR. So like 8. So 20 into 8 is like 160 plus there will be like transmission line, there will be like loads, there will be like reactive sources. So it will like go up to 400 plus states. We reduce these states to like 40 states, like 90% reduction. So in real time, we will be trying to actually lower the computational burden on our system. And if we are integrating wind farm to this Nordic gas system, we are now like increasing this. So this is like the in real world what actually is happening. Suppose we are having microgrid, we are having multiple DGs, each inverters, 10 to 20 states, and they are distributed controls. So these are like problem. Again, how to solve it? If we are having uh, what sort of study we are interested in? Are we interested in a regular model order reduction? Are we interested in robust? So if we have looked into detail actually. Without robustness, we have seen into 3 methods. So we can actually try to explore for a particular microgrid. Can we have a reduced model order? So if we are having a reduced model order, we need to validate our uh, reduced model order microgrid with the actual microgrid. At least we have to do one simulation where we have to design the complete microgrid. That burden on the RAM of the system has to be the we have to actually run that complete detailed model or detailed system and compare it with the reduced system. One of the 3 approaches we have seen earlier, we can use to reduce that microgrid. And then we have to show the dynamical behavior that the actual system and the reduced system is not deviating much, it is bounded, the dynamics are bounded. So these are like in real world application. This is like how we do in real world. So model order reduction is like, it is in the background of every system, it is now run. Because we do not need, it is by default run into the RTDA system, or we actually check that which states has to be preserved, which states have to be rejected, with the condition that we do not have so much deviation between the actual dynamics and the reduced dynamics. So like these are the future directions where we can explore it. We are actually in period for not that renewable integration has become the almost like day-to-day stuff. So we have renewable integration, we have very uh, large integration of electronic devices, we have like cyber physical systems, smart grids, real-time market. So these are the challenges that is now changing the dynamics of the system and how to take care of it. The next is like the since we have like went into these sensor base. So we have now uh, installed sensors at different locations. We are having so much data. We can now have a data-driven system. So how to have that data? Since the data volume of data is very large, can we have like a data-driven model or reduction? Can we have? Can we use some machine learning approaches? Again, this is structure preserving method. A lot of work has already been done, but can we explore these things into data-driven systems, non-linear or time-varying mode? So these are like some of the emerging areas of model order reduction techniques, and these are some uh, points where we can like explore it for a converter-based system. What is this? How can we actually say? If you look into our discussion, we said that we are studying model order reduction system for a linear system. Model order was reduced for a linear state space models only. However, the complete power system was non-linear, so we were linearizing at some point. So if you are doing this, there is a possibility that we may be off for a real-time study. Can we like adapt this model order reduction for a real-time study? Again, this is a research opportunity we can all look into. Can we have like distributed system? Therefore, distributed, can we have like distributed model order reduction techniques and model order reduction for discrete events and for this like quantum computing? So these are like points that can be explored and looked into. So what are the actually, so we have discussed some methods, we have discussed few examples, we have looked into some codes, very little and very simple codes. So what was our main objective? We actually not looked into the robust MOR, rather we have classical MOR. We looked classical MOR. We have looked into balanced transition, singular transition, model transition. So uh, there is like some is more suitable for like balanced transition, which are more suitable for general linear system. So it was like it preserves stability by default. It preserves. However, the single transition it was applicable for inter-area or rather multi-time escape, where we are having a very clear-cut demarcation between slow dynamics and fast dynamics. Model transition, we were looking into those participation factors where uh, we looked into that some of the states are contributing more into the dynamics as compared to the other states. So we were using that particular. So what are the like what method should we use for a particular approach? So it's a balanced method. It is best. It's a generally best suited. Balanced method is generally best suited. Or if it is multi-scale, and if we know that we are having a dynamics in the system, and the dynamics are like segregated into two parts. There is a fast dynamics, there is a slow dynamics. If we have like very clear-cut boundary between these, a clear-cut boundary we mean that a value sigma much less than one is exists. The ratio of these two dynamics, the time order, the time um, scale is much less than one. Ratio is much less than one. If we are having that condition, this single perturbation is an advantage for that system. And for if you are into studying the behavior of the system below certain or we want to take certain frequency and reject certain frequency, then model truncation or participation factor method is suitable. What should we do when we are actually doing this model order reduction? We must always validate our reduced model on full system. We must check whether our reduced model has uh, taken care of the stability. Whether our reduced model is stable or not, we must ensure it. We must actually show it actually. And then we need to actually monitor the performance metrics. Like we need to check whether the step response of the actual system and the reduced system is similar. The body plot of the actual system and the reduced system is similar. And we can also look into robustness. And certainly we have used this MATLAB to validate all those things. So what will be our approach for doing controller design? Controller design will be like we will be having a plan. We will be linearizing it with the sense that the model of reduction at this point of time, till we have a study, that we will be doing model order system on linearized model of the non-linear system. When we linearize it, we will reduce it, and then we will be designing the controller. The controller that is designed for reduced model will be validated on complete model. Complete model. So, how to reduce the model? Based upon the system characteristic, based upon constraints, based upon your overall system, whether it is single area system, multi-area system, are we having a clear-cut boundary between fast dynamics, slow dynamics, or general approach of this balanced transmission method. So we will be designing a controller for reduced orders. We will be using that standard method. A standard method means we can use those optimizations, beta heuristic optimizations to tune the controller parameters, and then we will be implementing it on complete non-linear systems. Again, this will be validated for the controller will be validated on original systems, and it will be shown the effect of controller on reduced system and on the original system has to be shown that both are performing satisfactorily and both are behaving satisfactorily in the almost similar way. So, what is the overall how you will check whether you have achieved your objectives or not? The controller, the reduced model, the controller design for reduced model is working for the complete model. Uh, this will be the benchmark for the success of our model order reduction. What we have actually looked into till this point of time is we have looked into what is the material foundation, three major model order reduction, how we are going into model order reduction for a single machine finite bar system. We have looked into some numericals. We have used some very small, simple script, and then we have like introduced you how these recent trends in these power system integration of renewable, integration of power electronics, more and more power electronics, how these are changing the introduction of large amount of sensors, large amount of data that is now fed into the fed into these like uh, SCADA centers where we are collecting all the data. How these are modifying the study of these systems, we have actually to uh, slightly look into these different areas. So this model of reduction is like a which is very important and very what you call as indispensable part of this research studies and is always done and is always a part of any available software package. So with this, I would like to conclude my discussion. So this was some of the if someone is interested, you can look into these few articles, and these are some of the MATLAB resources, functions, and the toolboxes that might be might someone might seem important if someone is going into this model order reduction. So with this, I would like to actually close my discussions, and I am happy to uh, uh, take some questions or discuss something if you have any.
Thank you so much, sir. Thank you on behalf of all the participants. I extend uh, Assistant Professor Dr. Ashim for deeply insightful session, and I would like to request all participants for any queries. Please unmute audio and ask your question for our esteemed speaker, Dr. Ashim, if any queries.
So this is my email ID. So if somebody uh, mm, might have some, or if you want to discuss or have some interaction, you can always mail me.
Sir, it appears no queries. And thank you again, sir.
Thank you. Thank you for
Thank you.
interview.
We are grateful for your time, decision, wisdom, and guidance. We look forward to engage with your